the most promising one. If you've ever been in any planning meeting, you know that planning is hard. As an important computational problem, planning is well studied and would require several volumes to cover. I'll only be able to cover the surface here. Planning overview. Given a task, there are many possible ways to decompose it, but not all of them will lead to a successful outcome. Among the correct solutions, some are more efficient than others. Consider the query: how many companies without revenue have raised at least $1 billion? There are many possible ways to solve this, but as an illustration, consider the two options. 1. Find all companies without revenue, then filter them by the amount raised. 2. Find all companies that have raised at least $1 billion, then filter them by revenue. The second option is more efficient. There are vastly more companies without revenue than companies that have raised $1 billion. Given only these two options, an intelligent agent should choose option 2. You can couple planning with execution in the same prompt. For example, you give the model a prompt, ask it to think step by step, such as with a chain of thought prompt, and then execute those steps all in one prompt. But what if the model comes up with a 1,000-step plan that doesn't even accomplish the goal? Without oversight, an agent can run those steps for hours, wasting time and money on API calls, before you realize that it's not going anywhere. To avoid fruitless execution, planning should be decoupled from execution. You ask the agent to first generate a plan, and only after this plan is validated is it executed. The plan can be validated using heuristics. For example, one simple heuristic is to eliminate plans with invalid actions. If the generated plan requires a Google search and the agent doesn't have access to Google search, this plan is invalid. Another SIM/PLE heuristic might be eliminating all plans with more than X steps. A plan can also be validated using AI judges. You can ask a model to evaluate whether the plan seems reasonable or how to improve it. If the generated plan is evaluated to be bad, you can ask the planner to generate another plan. If the generated plan is good, execute it. If the plan consists of external tools, function calling will be invoked. Outputs from executing this plan will then again need to be evaluated. Note that the generated plan doesn't have to be in 282, Chapter 6, RAG and Agents. 12. Because most agentic workflows are sufficiently complex to involve multiple components, most agents are multi-agent. End-to-end plan for the whole task. It can be a small plan for a subtask. The whole process looks like Figure 6.9. Figure 6.9. Decoupling planning and execution so that only validated plans are executed. Your system now has 3 components, one to generate plans, one to validate plans, and another to execute plans. If you consider each component an agent, this is a multi-agent system. 12. To speed up the process, instead of generating plans sequentially, you can generate several plans in parallel and ask the evaluator to pick the most promising one. This is another latency/cost trade-off, as generating multiple plans simultaneously will incur extra costs. Planning requires understanding the intention behind a task. What's the user trying to do with this query? An intent classifier is often used to help agents plan. As shown in Break Complex Tasks into Simpler Subtasks on page 224, intent classification can be done using another prompt or a classification model trained for this task. The intent classification mechanism can be considered another agent in your multi-agent system. Knowing the intent can help the agent pick the right tools. For example, for customer support, if the query is about billing, the agent might need access to a tool to retrieve a user's recent payments. But if the query is about how to reset a password, the agent might need to access documentation retrieval. Agents 283. Some queries might be out of the scope of the agent. The intent classifier should be able to classify requests as irrelevant so that the agent can politely reject those instead of wasting flops coming up with impossible solutions. So far, we've assumed that the agent automates all 3 stages: generating plans, validating plans, and executing plans. In reality, humans can be involved at any of those stages to aid with the process and mitigate risks. A human expert can provide a plan, validate a plan, or execute parts of a plan. For example, for complex tasks for which an agent has trouble generating the whole plan, a human expert can provide a high-level plan that the agent can expand upon. If a plan involves risky operations, such as updating a database or merging a code change, the system can ask for explicit human approval before executing or let humans execute these operations. To make this possible, you need to clearly define the level of automation an agent can have for each action. To summarize, solving a task typically involves the following processes. Note that reflection isn't mandatory for an agent, but it'll significantly boost the agent's performance. 1. Plan generation. Come up with a plan for accomplishing this task. A plan is a sequence of manageable actions, so this process is also called task decomposition. 2. Reflection and error correction. Evaluate the generated plan. If it's a bad plan, generate a new one. 3. Execution. Take the actions outlined in the generated plan. This often involves calling specific functions. 4. Reflection and error correction. Upon receiving the action outcomes, evaluate these outcomes and determine whether the goal has been accomplished. Identify and correct mistakes. If the goal is not completed, generate a new plan. You've already seen some techniques for plan generation and reflection in this book. When you ask a model to think step by step, you're asking it to decompose a task. When you ask a model to verify if your answer is correct, you're asking it to reflect. Foundation models as planners. An open question is how well foundation models can plan. Many researchers believe that foundation models, at least those built on top of autoregressive language models, cannot. Meta's chief AI scientist Yann LeCun states unequivocally that autoregressive LLMs can't plan, 2023. In the article, Can LLMs Really Reason and Plan? Kambampati, 2023, argues that LLMs are great at extracting knowledge but not planning. Kambampati suggests that the papers claiming planning abilities of LLMs confuse general planning knowledge extracted from the LLMs with executable plans. 284. Chapter 6, RAG and Agents. The plans that come out of LLMs may look reasonable to the lay user, and yet lead to execution time interactions and errors. However, while there is a lot of anecdotal evidence that LLMs are poor planners, it's unclear whether it's because we don't know how to use LLMs the right way or because LLMs, fundamentally, can't plan. Planning, at its core, is a search problem. You search among different paths to the goal, predict the outcome, reward, of each path, and pick the path with the most promising outcome. Often, you might determine that no path exists that can take you to the goal. Search often requires backtracking. For example, imagine you're at a step where there are two possible actions, A and B. After taking action A, you enter a state that's not promising, so you need to backtrack to the previous state to take action B. Some people argue that an autoregressive model can only generate forward actions. It can't backtrack to generate alternate actions. Because of this, they conclude that autoregressive models can't plan. However, this isn't necessarily true. After executing a path with action A, if the model determines that this path doesn't make sense, it can revise the path using action B instead, effectively backtracking. The model can also always start over and choose another path. It's also possible that LLMs are poor planners because they aren't given the toolings needed to plan. To plan, it's necessary to know not only the available actions but also the potential outcome of each action. As a simple example, let's say you want to walk up a mountain. Your potential actions are turn right, turn left, turn around, or go straight ahead. However, if turning right will cause you to fall off the cliff, you might not want to consider this action. In technical terms, an action takes you from one state to another, and it's necessary to know the outcome state to determine whether to take an action. This means it's not sufficient to prompt a model to generate only a sequence of actions like what the popular chain of thought prompting technique does. The paper Reasoning with Language Model is Planning with World Model, How et al., 2023, argues that an LLM, by containing so much information about the world, is capable of predicting the outcome of each action. This LLM can incorporate this outcome prediction to generate coherent plans. Even if AI can't plan, it can still be a part of a planner. It might be possible to augment an LLM with a search tool and state tracking system to help it plan. Agents 285. Foundation Model, FM, versus Reinforcement Learning, RL. Planners. The agent is a core concept in RL, which is defined in Wikipedia as a field concerned with how an intelligent agent ought to take actions in a dynamic environment in order to maximize the cumulative reward. RL agents and FM agents are similar in many ways. They are both characterized by their environments and possible actions. The main difference is in how their planners work. In an RL agent, the planner is trained by an RL algorithm. Training this RL planner can require a lot of time and resources. In an FM agent, the model is the planner. This model can be prompted or fine-tuned to improve its planning capabilities, and generally requires less time and fewer resources. However, there's nothing to prevent an FM agent from incorporating RL algorithms to improve its performance. I suspect that in the long run, FM agents and RL agents will merge. Plan generation. The simplest way to turn a model into a plan generator is with prompt engineering. Imagine that you want to create an agent to help customers learn about products at Kitty Vogue. You give this agent access to 3 external tools: retrieve products by price, retrieve top products, and retrieve product information. Here's an example of a prompt for plan generation. This prompt is for illustration purposes only. Production prompts are likely more complex. System prompt: propose a plan to solve the task. You have access to 5 actions: get _today_date, fetch _top products, start _date, end _date, number _products, fetch _product_info, product _name, generate _query, task _history, tool _output, generate _response, query. The plan must be a sequence of valid actions. Examples: task: tell me about Fruity Fedora. Plan: fetch _product_info, generate _query, generate _response. Task: what was the best-selling product last week? Plan: fetch _top products, generate _query, generate _response. 286, Chapter 6, RAG and Agents. Task: user input. Plan: there are 2 things to note about this example. The plan format used here, a list of functions whose parameters are inferred by the agent, is just one of many ways to structure the agent control flow. The generate _query function takes in the task's current history and the most recent tool outputs to generate a query to be fed into the response generator. The tool output at each step is added to the task's history. Given the user input, what's the price of the best-selling product last week? A generated plan might look like this: 1. Get _time, 2. Fetch _top products, 3. Fetch _product_info, 4. Generate _query, 5. Generate _response. You might wonder, what about the parameters needed for each function? The exact parameters are hard to predict in advance since they are often extracted from the previous tool outputs. If the first step, get _time, outputs September 13, 2030, then the agent can reason that the parameters for the next step should be called with the following parameters: retrieve _top products, start _date equals 2030-09-07, end _date equals 2030-09-13, number _products equals 1. Often, there's insufficient information to determine the exact parameter values for a function. For example, if a user asks, what's the average price of best-selling products? The answers to the following questions are unclear. How many best-selling products does the user want to look at? Does the user want the best-selling products last week, last month, or of all time? This means that models frequently have to guess, and guesses can be wrong. Because both the action sequence and the associated parameters are generated by AI models, they can be hallucinated. Hallucinations can cause the model to call an invalid function or call a valid function but with wrong parameters. Techniques for improving a model's performance in general can be used to improve a model's planning capabilities. Agents 287. Here are a few approaches to make an agent better at planning. Write a better system prompt with more examples. Give better descriptions of the tools and their parameters so that the model understands them better. Rewrite the functions themselves to make them simpler, such as refactoring a complex function into two simpler functions. Use a stronger model. In general, stronger models are better at planning. Fine-tune a model for plan generation. Function calling. Many model providers offer tool use for their models, effectively turning their models into agents. A tool is a function. Invoking a tool is, therefore, often called function calling. Different model APIs work differently, but in general, function calling works as follows. 1. Create a tool inventory. Declare all the tools that you might want a model to use. Each tool is described by its execution entry point, e.g., its function name, its parameters, and its documentation, e.g., what the function does and what parameters it needs. 2. Specify what tools the agent can use. Because different queries might need different tools, many APIs let you specify a list of declared tools to be used per query. Some let you control tool use further by the following settings. Required: the model must use at least one tool. None: the model shouldn't use any tool. Auto: the model decides which tools to use. Function calling is illustrated in Figure 6.10. This is written in pseudocode to make it representative of multiple APIs. To use a specific API, please refer to its documentation. 288, Chapter 6, RAG and Agents. Figure 6.10. An example of a model using two simple tools. Given a query, an agent defined as in Figure 6.10 will automatically generate what tools to use and their parameters. Some function calling APIs will make sure that only valid functions are generated, though they won't be able to guarantee the correct parameter values. For example, given the user query, how many kilograms are 40 pounds, the agent might decide that it needs the tool lbs_2_kg_ tool with one parameter value of 40. The agent's response might look like this: response equals model response, finish_reason equals tool_calls, message equals chat. Message, content equals none, role equals assistant, tool_calls sad face tool call, function equals function, arguments equals, lbs 40, name equals lbs_2_kg, type equals function, agents 289. From this response, you can evoke the function lbs_2_kg, lbs equals 40, and use its output to generate a response to the users. When working with agents, always ask the system to report what parameter values it uses for each function call. Inspect these values to make sure they are correct. Planning granularity. A plan is a roadmap outlining the steps needed to accomplish a task. A roadmap can be of different levels of granularity. To plan for a year, a quarter-by-quarter plan is higher level than a month-by-month plan, which is, in turn, higher level than a week-to-week plan. There's a planning/execution trade-off. A detailed plan is harder to generate but easier to execute. A higher-level plan is easier to generate but harder to execute. An approach to circumvent this trade-off is to plan hierarchically. First, use a planner to generate a high-level plan, such as a quarter-to-quarter plan. Then, for each quarter, use the same or a different planner to generate a month-to-month plan. So far, all examples of generated plans use the exact function names, which is very granular. A problem with this approach is that an agent's tool inventory can change over time. For example, the function to get the current date get_time can be renamed to get_current_time. When a tool changes, you'll need to update your prompt and all your examples. Using the exact function names also makes it harder to reuse a planner across different use cases with different tool APIs. If you've previously fine-tuned a model to generate plans based on the old tool inventory, you'll need to fine-tune the model again on the new tool inventory. To avoid this problem, plans can also be generated using a more natural language, which is higher level than domain-specific function names. For example, given the query, "What's the price of the best-selling product last week?" an agent can be instructed to output a plan that looks like this: 1. Get current date. 2. Retrieve the best-selling product last week. 3. Retrieve product information 4. Generate query 5. Generate response 290 Chapter 6, RAG and Agents. 13 Chameleon, Liu et al., 2023, calls this translator a program generator. Using more natural language helps your plan generator become robust to changes in tool APIs. If your model was trained mostly on natural language, it'll likely be better at understanding and generating plans in natural language and less likely to hallucinate. The downside of this approach is that you need a translator to translate each natural language action into executable commands. 13 However, translating is a much simpler task than planning and can be done by weaker models with a lower risk of hallucination. Complex plans. The plan examples so far have been sequential. The next action in the plan is always executed after the previous action is done. The order in which actions can be executed is called a control flow. The sequential form is just one type of control flow. Other types of control flows include the parallel, if statement, and for loop. The following list provides an overview of each control flow, including sequential for comparison. Sequential executing task B after task A is complete, likely because task B depends on task A. For example, the SQL query can be executed only after it's been translated from the natural language input. Parallel executing tasks A and B at the same time. For example, given the query, find me best-selling products under $100, an agent might first retrieve the top 100 best-selling products and, for each of these products, retrieve its price. If statement executing task B or task C depending on the output from the previous step. For example, the agent first checks NVIDIA's earnings report. Based on this report, it can then decide to sell or buy NVIDIA stocks. For loop, repeat executing task A until a specific condition is met. For example, keep on generating random numbers until a prime number. These different control flows are visualized in Figure 6:11. Agents 291. Figure 6:11. Examples of different orders in which a plan can be executed. In traditional software engineering, conditions for control flows are exact. With AI-powered agents, AI models determine control flows. Plans with non-sequential control flows are more difficult to both generate and translate into executable commands. When evaluating an agent framework, check what control flows it supports. For example, if the system needs to browse 10 websites, can it do so simultaneously? Parallel execution can significantly reduce the latency perceived by users. Reflection and error correction. Even the best plans need to be constantly evaluated and adjusted to maximize their chance of success. While reflection isn't strictly necessary for an agent to operate, it's necessary for an agent to succeed. Reflection can be useful in many places during a task process, after receiving a user query to evaluate if the request is feasible. After the initial plan generation to evaluate whether the plan makes sense. After each execution step to evaluate if it's on the right track. After the whole plan has been executed to determine if the task has been accomplished. 292, Chapter 6, RAG and Agents. 14 This reminds me of the actor-critic AC, agent method, Conda and Tsitsiklis, 1999, in Reinforcement Learn ing. Reflection and error correction are two different mechanisms that go hand in hand. Reflection generates insights that help uncover errors to be corrected. Reflection can be done with the same agent using self-critique prompts. It can also be done with a separate component, such as a specialized scorer, a model that outputs a concrete score for each outcome. First proposed by React, Yao et al., 2022, interleaving reasoning and action has become a common pattern for agents. Yao et al. Used the term reasoning to encompass both planning and reflection. At each step, the agent is asked to explain its thinking, planning, take actions, then analyze observations, reflection, until the task is considered finished by the agent. The agent is typically prompted, using exam please, to generate outputs in the following format: Thought 1. Act 1. Observation 1. Continue until reflection determines that the task is finished. Thought N. Act N, Finish, Response to Query, Figure 6, 12 shows an example of an agent following the React framework respond ing to a question from Hotpot QA, Yang et al., 2018, a benchmark for multi-hop question answering. You can implement reflection in a multi-agent setting. One agent plans and takes actions, and another agent evaluates the outcome after each step or after a number of steps. 14. If the agent's response failed to accomplish the task, you can prompt the agent to reflect on why it failed and how to improve. Based on this suggestion, the agent generates a new plan. This allows agents to learn from their mistakes. For example, given a coding generation task, an evaluator might evaluate that the generated code fails 1/3 of test cases. The agent then reflects the reason it failed is because it didn't take into account arrays where all numbers are negative. The actor then generates new code, taking into account all negative arrays. Agents 293. Figure 6, 12. A React agent in action. Image from the React paper, Yao et al., 2022. The image is licensed under CC by 4.0. This is the approach that Reflection, Shin et al., 2023, took. In this framework, reflection is separated into two modules, an evaluator that evaluates the outcome and a self-reflection module that analyzes what went wrong. Figure 6, 13 shows examples of reflection agents in action. The authors used the term trajectory to refer to a plan. At each step, after evaluation and self-reflection, the agent proposes a new trajectory. Compared to plan generation, reflection is relatively easy to implement and can bring surprisingly good performance improvement. The downside of this approach is latency and cost. Thoughts, observations, and sometimes actions can take a lot of tokens to generate, which increases cost and user-perceived latency, especially for tasks with many intermediate steps. To nudge their agents to follow the format, both React and Reflection authors used plenty of examples in their prompts. This increases the cost of computing input tokens and reduces the context space available for other information. 294, Chapter 6, RAG and Agents. Figure 6, 13. Examples of how reflection agents work. Images from the Reflection GitHub repo. Tool selection. Because tools often play a crucial role in a task's success, tool selection requires careful consideration. The tools to give your agent depend on the environment and the task, but they also depend on the AI model that powers the agent. There's no foolproof guide on how to select the best set of tools. Agent literature consists of a wide range of tool inventories. For example, Toolformer, Schick et al., 2023, fine-tune GPT-J to learn 5 tools. Chameleon, Liu et al., 2023, uses 13 tools. On the other hand, Gorilla, Patil et al., 2023, attempted to prompt agents to select the right API call among 1,645 APIs. More tools give the agent more capabilities. However, the more tools there are, the harder it is to efficiently use them. It's similar to how it's harder for humans to master a large set of tools. Adding tools also means increasing tool descriptions, which might not fit into a model's context. Like many other decisions while building AI applications, tool selection requires experimentation and analysis. Here are a few things you can do to help you decide. Compare how an agent performs with different sets of tools. Do an ablation study to see how much the agent's performance drops if a tool is removed from its inventory. If a tool can be removed without a performance drop, remove it. Agents 295. Look for tools that the agent frequently makes mistakes on. If a tool proves too hard for the agent to use, for example, extensive prompting and even fine-tuning can't get the model to learn to use it, change the tool. Plot the distribution of tool calls to see what tools are most used and what tools are least used. Figure 6, 14 shows the differences in tool use patterns of GPT-4 and ChatGPT in Chameleon, Liu et al., 2023. Figure 6, 14. Different models and tasks express different tool use patterns. Image from Liu et al. 2023, adapted from an original image licensed under CC by 4.0. Experiments by Liu et al. 2023 also demonstrate 2 points. 1. Different tasks require different tools. Science QA, the science question-answer ing task, relies much more on knowledge retrieval tools than TabMWP, a tabular math problem-solving task. 2. Different models have different tool preferences. For example, GPT-4 seems to select a wider set of tools than ChatGPT. ChatGPT seems to favor image caption ing, while GPT-4 seems to favor knowledge retrieval. When evaluating an agent framework, evaluate what planners and tools it supports. Different frameworks might focus on different categories of tools. For example, AutoGPT focuses on social media APIs, Reddit, X, and Wikipedia, whereas Composio focuses on enterprise APIs, Google Apps, GitHub, and Slack. As your needs will likely change over time, evaluate how easy it is to extend your agent to incorporate new tools. 296, Chapter 6, RAG and Agents. As humans, we become more productive not just by using the tools we're given, but also by creating progressively more powerful tools from simpler ones. Can AI create new tools from its initial tools? Chameleon, Liu et al., 2023, proposes the study of tool transition. After tool X, how likely is the agent to call tool Y? Figure 6.15 shows an example of tool transition. If two tools are frequently used together, they can be combined into a bigger tool. If an agent is aware of this information, the agent itself can combine initial tools to continually build more complex tools. Figure 6.15. A tool transition tree by Liu et al. 2023, adapted from an original image licensed under CC by 4.0. Vogager, Wang et al., 2023, proposes a skill manager to keep track of new skills, tools, that an agent acquires for later reuse. Each skill is a coding program. When the skill manager determines a newly created skill is to be useful, e.g., because it successfully helped an agent accomplish a task, it adds this skill to the skill library, conceptually similar to the tool inventory. This skill can be retrieved later to use for other tasks. Agents 297. Earlier in this section, we mentioned that the success of an agent in an environment depends on its tool inventory and its planning capabilities. Failures in either aspect can cause the agent to fail. The next section will discuss different failure modes of an agent and how to evaluate them. Agent failure modes and evaluation. Evaluation is about detecting failures. The more complex a task an agent performs, the more possible failure points there are. Other than the failure modes common to all AI applications discussed in chapters 3 and 4, agents also have unique failures caused by planning, tool execution, and efficiency. Some of the failures are easier to catch than others. To evaluate an agent, identify its failure modes and measure how often each of these failure modes happens. I created a simple benchmark to illustrate these different failure modes that you can see on the book's GitHub repository. There are also agent benchmarks and leaderboards such as the Berkeley function calling leaderboard, the AgentOps evaluation harness, and the travel planner benchmark. Planning failures. Planning is hard and can fail in many ways. The most common mode of planning failure is tool use failure. The agent might generate a plan with one or more of these errors. Invalid tool, for example, it generates a plan that contains Bing_search, but Bing_search isn't in the agent's tool inventory. Valid tool, invalid parameters. For example, it calls lbs_to_kg with two parameters. lbs_to_kg is in the tool inventory but requires only one parameter, lbs. Valid tool, incorrect parameter values. For example, it calls lbs_to_kg with one parameter, lbs, but uses the value 100 for lbs when it should be 120. Another mode of planning failure is goal failure. The agent fails to achieve the goal. This can be because the plan doesn't solve a task, or it solves the task without follow the constraints. To illustrate this, imagine you ask the model to plan a 2-week trip from San Francisco to Hanoi with a budget of $5,000. The agent might plan a trip from San Francisco to Ho Chi Minh City, or plan a 2-week trip from San Francisco to Hanoi that will be way over the budget. 298 Chapter 6, RAG and Agents. A common constraint that is often overlooked by agent evaluation is time. In many cases, the time an agent takes matters less, because you can assign a task to an agent and only need to check in when it's done. However, in many cases, the agent becomes less useful with time. For example, if you ask an agent to prepare a grant proposal and the agent finishes it after the grant deadline, the agent isn't very helpful. An interesting mode of planning failure is caused by errors in reflection. The agent is convinced that it's accomplished a task when it hasn't. For example, you ask the agent to assign 50 people to 30 hotel rooms. The agent might assign only 40 people and insist that the task has been accomplished. To evaluate an agent for planning failures, one option is to create a planning dataset where each example is a tuple, task, tool inventory. For each task, use the agent to generate a k number of plans. Compute the following metrics. 1. Out of all generated plans, how many are valid? 2. For a given task, how many plans does the agent have to generate, on average, to get a valid plan? 3. Out of all tool calls, how many are valid? 4. How often are invalid tools called? 5. How often are valid tools called with invalid parameters? 6. How often are valid tools called with incorrect parameter values? Analyze the agent's outputs for patterns. What types of tasks does the agent fail more on? Do you have a hypothesis why? What tools does the model frequently make mistakes with? Some tools might be harder for an agent to use. You can improve an agent's ability to use a challenging tool by better prompting, more examples, or fine-tuning. If all fail, you might consider swapping this tool for something easier to use. Tool failures happen when the correct tool is used, but the tool output is wrong. One failure mode is when a tool just gives the wrong outputs. For example, an image captionier returns a wrong description, or an SQL query generator returns a wrong SQL query. If the agent generates only high-level plans and a translation module is involved in translating from each planned action to executable commands, failures can happen because of translation errors. Agents 299. Tool failures can also happen because the agent doesn't have access to the right tools for the task. An obvious example is when the task involves retrieving the current stock prices from the internet, and the agent doesn't have access to the internet. Tool failures are tool-dependent. Each tool needs to be tested independently. Always print out each tool call and its output so that you can inspect and evaluate them. If you have a translator, create benchmarks to evaluate it. Detecting missing tool failures requires an understanding of what tools should be used. If your agent frequently fails on a specific domain, this might be because it lacks tools for this domain. Work with human domain experts and observe what tools they would use. Efficiency: an agent might generate a valid plan using the right tools to accomplish a task, but it might be inefficient. Here are a few things you might want to track to evaluate an agent's efficiency. How many steps does the agent need, on average, to complete a task? How much does the agent cost, on average, to complete a task? How long does each action typically take? Are there any actions that are especially time-consuming or expensive? You can compare these metrics with your baseline, which can be another agent or a human operator. When comparing AI agents to human agents, keep in mind that humans and AI have very different modes of operations, so what's considered efficient for humans might be inefficient for AI, and vice versa. For example, visiting 100 web pages might be inefficient for a human agent who can visit only one page at a time, but trivial for an AI agent that can visit all the web pages at once. In this chapter, we've discussed in detail how RAG and agent systems function. Both patterns often deal with information that exceeds a model's context limit. A memory system that supplements the model's context in handling information can significantly enhance its capabilities. Let's now explore how a memory system works. Memory refers to mechanisms that allow a model to retain and utilize information. A memory system is especially useful for knowledge-rich applications like RAG and multi-step applications like agents. A RAG system relies on memory for its augmented context, which can grow over multiple turns as it retrieves more information. An agentic system needs memory to store instructions, examples, context, tool invento rise, plans, tool outputs, reflections, and more. While RAG and agents place greater 300 Chapter 6, RAG and agents demands on memory, it is beneficial for any AI application that requires retaining information. An AI model typically has three main memory mechanisms. Internal knowledge. The model itself is a memory mechanism, as it retains the knowledge from the data it was trained on. This knowledge is its internal knowledge. A model's internal knowledge doesn't change unless the model itself is updated. The model can access this knowledge in all queries. Short-term memory. A model's context is a memory mechanism. Previous messages in a conversation can be added to the model's context, allowing the model to leverage them to generate future responses. A model's context can be considered its short-term memory as it doesn't persist across tasks, queries. It's fast to access, but its capacity is limited. Therefore, it's often used to store information that is most important for the current task. Long-term memory. External data sources that a model can access via retrieval, such as an RAG system, are a memory mechanism. This can be considered the model's long-term memory, as it can be persisted across tasks. Unlike a model's internal knowledge, information in the long-term memory can be deleted without updating the model. Humans have access to similar memory mechanisms. How to breathe is your internal knowledge. You typically don't forget how to breathe unless you're in serious trouble. Your short-term memory contains information immediately relevant to what you're doing, such as the name of a person you just met. Your long-term memory is augmented with books, computers, notes, etc. Which memory mechanism to use for your data depends on its frequency of use. Information essential for all tasks should be incorporated into the model's internal knowledge via training or fine-tuning. Information that is rarely needed should reside in its long-term memory. Short-term memory is reserved for immediate, context-specific information. These three memory mechanisms are illustrated in Figure 6:16. Memory 301. Figure 6:16. The hierarchy of information for an agent. Memory is essential for humans to operate. As AI applications have evolved, developers have quickly realized that memory is important for AI models, too. Many memory management tools for AI models have been developed, and many model providers have incorporated external memory. Augmenting an AI model with a memory system has many benefits. Here are just a few of them. Manage information overflow within a session. During the process of executing a task, an agent acquires a lot of new information, which can exceed the agent's maximum context length. The excess information can be stored in a memory system with long-term memories. Persist information between sessions. An AI coach is practically useless if every time you want the coach's advice, you have to explain your whole life story. An AI assistant would be annoying to use if it keeps forgetting your preferences. Having access to your conversation history can allow an agent to personalize its actions to you. For example, when you ask for book recommendations, if the model remembers that you previously loved The Three-Body Problem, it can suggest similar books. Boost a model's consistency. If you ask me a subjective question twice, like rating a joke between 1 and 5, I'm much more likely to give consistent answers if I remember my previous answer. Similarly, if an AI model can reference its previous answers, it can calibrate its future answers to be consistent. 302, Chapter 6, RAG and Agents. Maintain data structural integrity. Because text is inherently unstructured, the data stored in the context of a text-based model is unstructured. You can put structured data in the context. For example, you can feed a table into the context line by line, but there's no guarantee that the model will understand that this is supposed to be a table. Having a memory system capable of storing structured data can help maintain the structural integrity of your data. For example, if you ask an agent to find potential sales leads, this agent can leverage an Excel sheet to store the leads. An agent can also leverage a queue to store the sequence of actions to be performed. A memory system for AI models typically consists of two functions: memory management, managing what information should be stored in the short-term and long-term memory. Memory retrieval, retrieving information relevant to the task from long-term memory. Memory retrieval is similar to RAG retrieval, as long-term memory is an external data source. In this section, I'll focus on memory management. Memory management typically consists of two operations: add and delete memory. If memory storage is limited, deletion might not be necessary. This might work for long-term memory because external memory storage is relatively cheap and easily extensible. However, short-term memory is limited by the model's maximum context length and, therefore, requires a strategy for what to add and what to delete. Long-term memory can be used to store the overflow from short-term memory. This operation depends on how much space you want to allocate for short-term memory. For a given query, the context input into the model consists of both its short-term memory and information retrieved from its long-term memory. A model's short-term capacity is, therefore, determined by how much of the context should be allocated for information retrieved from long-term memory. For example, if 30% of the context is reserved, then the model can use at most 70% of the context limit for short-term memory. When this threshold is reached, the overflow can be moved to long-term memory. Like many components previously discussed in this chapter, memory management isn't unique to AI applications. Memory management has been a cornerstone of all data systems, and many strategies have been developed to use memory efficiently. The simplest strategy is FIFO, first in, first out. The first to be added to the short-term memory will be the first to be moved to the external storage. As a conversation gets longer, API providers like OpenAI might start removing the beginning of the conversation. Frameworks like LangChain might allow the retention of n-last MES sages or n-last tokens. In a long conversation, this strategy assumes that the early memory 303. 15 for human conversations, the opposite might be true if the first few messages are pleasantries. 16 usage-based strategies, such as removing the least frequently used information, is more challenging, since you'll need a way to know when a model uses a given piece of information. Messages are less relevant to the current discussion. However, this assumption can be fatally wrong. In some conversations, the earliest messages might carry the most information, especially when the early messages state the purpose of the converse tie-in. 15 While FIFO is straightforward to implement, it can cause the model to lose track of important information. 16 More sophisticated strategies involve removing redundancy. Human languages contain redundancy to enhance clarity and compensate for potential misunderstandings. If there's a way to automatically detect redundancy, the memory footprint will be reduced significantly. One way to remove redundancy is by using a summary of the conversation. This summary can be generated using the same or another model. Summarization, together with tracking named entities, can take you a long way. Bay et al. 2022 took this a step further. After obtaining the summary, the authors wanted to construct a new memory by joining the memory with the key information that the summary missed. The authors developed a classifier that, for each sentence in the memory and each sentence in the summary, determines if only one, both, or neither should be added to the new memory. Liu et al. 2023, on the other hand, used a reflection approach. After each action, the agent is asked to do two things. 1. Reflect on the information that has just been generated. 2. Determine if this new information should be inserted into the memory, should merge with the existing memory, or should replace some other information, especially if the other information is outdated and contradicts new information. When encountering contradicting pieces of information, some people opt to keep the newer ones. Some people ask AI models to judge which one to keep. How to handle contradiction depends on the use case. Having contradictions can cause an agent to be confused but can also help it draw from different perspectives. 304, Chapter 6, RAG and Agents. Summary. Given the popularity of RAG and the potential of agents, early readers have mentioned that this is the chapter they're most excited about. This chapter started with RAG, the pattern that emerged first between the two. Many tasks require extensive background knowledge.